Google start பண்ணலாமா?
2 minutes sir.
4:50 தானே? All are available. Hello. Good evening, Professor Thomas. I think Thomas, sir.
Yes, I'm here. I'm
Yes,
here.
sir. Yes, sir. Okay,
Yeah.
okay.
Just
Sir,
trying
I
to.
think, yeah, that all the speakers available, sir, including inviter speaker.
One minute. Try to reconnect because I have some issues.
Okay, sir. We will wait.
Okay, I can.
Hello. Good evening to one and all. Myself, G. Bhakyaraj, Assistant Professor, Department of Physics and Nanotechnology, SRM IST. Welcome to this second day of section 4F, Nanostructured Solar Cell and Thermoelectrics. In this session, we have one invited lecture in the field of thermoelectric materials and devices by Dr. M. Navanithan, SRM IST, and 3 contributory lectures. Before going to start the session, I am happy to introduce session chair, Professor Thomas Anthopoulos, Material Science and Engineering, Physical Science and Engineering Division, King Abdullah University of Science and Technology, Saudi Arabia. His research interests are devices physics, large area electronics and material engineering for solar application, and electronics also, that is a large area thin film electronics. And awards and achievement, he obtained a Marie Curie postdoctoral fellowship in 2003 to 2006, Philips Research Laboratories, Netherlands, and a postdoctoral fellowship in 2001 to 2003, University of St. Andrews, Scotland. He has published a high value paper in many Nature Publishing Group journals and advanced materials. His paper citation around 22,000 and H index is 74. Now I invite Professor Thomas Anthopoulos to be a session chair.
Great, thank you very much for the very kind introduction. It is a great honor to chair this session, and we have, as already mentioned, the first invited speaker, Professor Navanithan. And I will talk about the thermoelectrics topic we have already covered. Dr. Navanithan is quite prolific in his research. He's interested in multifunctional nanostructure materials and applications, as well as solar cells, dye-sensitized, and more recent developments like perovskite solar cells and nanostructure thermoelectrics. He has received a number of awards. He's a visiting professor, as you can see, in a number of institutions. He's published extensively with a citation count of over 2,500 and an H index of 27. I'm very much interested to listen to the talk and to the latest developments. So, Dr. Navanithan, please go ahead with your talk on layered thermoelectric materials and devices.
Thank you, Professor Thomas. It's a great pleasure to have you here, and thank you for your kind introduction. So let me share the screen first.
Make sure I ring the bell at the 22nd minute, and then at 25th minute, we will try to stop, follow with some question and answer session.
Yeah, fine. Yeah.
Great, thank you.
Thank you. So I thank the organizers for giving me this opportunity to deliver the invited talk in the ICONN 2021. So today I'm going to talk about the layered thermoelectrics materials and devices and what we are doing it in our group at SRM IST about thermoelectrics. So as we all know that like Professor Kanishka Biswas extensively gave a talk on thermoelectrics of various materials, but I'm going to bit cover about the layered thermoelectric materials. For examples, we extensively study like molybdenum disulfide, like thick and bulk material, and then tin telluride, bismuth 2, selenium 3, and then PANI as well as graphene oxide. And I'll also a little bit cover about the PH2TE3 wearable thermoelectric devices which we made in our laboratory. So as you know that anyway, the people are like looking for the alternative energy resources in recent years due to the industrial development. So anyway, the research on like conversion of energy to the electrical energy taking place in various fields like solar cells to nuclear energy, then so on. However, very recently the thermoelectric research has been a very hot topic to find out the way to use the heat as a source to produce the electricity. For example, there are more than 30 or 40% of the heat is wasted. Like those heat can be effectively used to produce the electricity by so-called thermoelectric effect. So as you are very aware that this field is not new in terms of fundamental aspects. For example, the Seebeck effect was discovered in the year late 18th century. So let me introduce like what is thermoelectric generator. For example, thermoelectric generator is combining of two N and P type legs. At one end you apply the heat and other end you apply a cold. The temperature gradient will give the thermo EMF. So that gives you the electrical signal. So how you define a material can be used into thermoelectric. So that is very important. For example, here I can tell you that the ZT, that is the figure of merit, can be defined by means of the square of Seebeck coefficient with respect to the electrical conductivity by that total thermal conductivity, that is electronic as well as the lattice contribution of thermal conductivity at absolute temperature. So these parameters gives you the value of figure of merit. So this figure of merit literally plays a role in finding out the thermoelectric efficiency of a particular device. For example, in general, if a material having the ZT of above 1, then they are considered to be best thermoelectric material. If the materials are exhibiting over 3 to 4 ZT, then they can be taken to the commercializations. So this ZT to 3 to 4, in experimentally, it is not that easy. Theoretically, people have proven. However, there are only few materials have been given as the ZT of over 3 to 4. So what are the challenges one can come across the increasing in the figure of merit? For example, these three parameters are interdependent. As I already mentioned, this electrical conductivity as well as the Seebeck coefficient. Seebeck coefficient as well as the thermal conductivity, these three parameters are interdependent. For example, if you take the metal, semiconductor as well as the insulators, the metal has more thermal conductivity as well as the electrical conductivity. So this is a very compromising factor. If one increases and if others decreases, then it is not giving a good CT. So we need to have an optimized value of both Seebeck as well as thermal conductivity and electrical conductivity. So how to overcome this? For example, let me talk about the increasing the electrical conductivity as well as the Seebeck coefficient. Here, we can do by having the energy filtering effect. What is the energy filtering effect? The energy filtering effect is nothing but you can localize the electrons with the energy, like it depends upon the energy. So you can have the like you can filter out the electrons which are like low energy or high energy based on the medium, so that we can enhance the electrical conductivity. And the second is how to lower thermal conductivity. Here you can use the all-scale hierarchical architectures. It means that you should have more number of grain boundaries where you can scatter the electrons. That time it can release the phonon, like the heat. That phonon carries the heat, so therefore we can lower the thermal conductivity by having more amount of grain boundaries. And in addition to the grain boundary, we can have the nanoprecipitates. So these precipitates will act as the scattering centers to lower the thermal conductivity. And the next one is the modulation of doping. In modulation of doping, two things can be taken place. That is, one is the increasing of electrical conductivity, and moreover, it will also go in decreasing the thermal conductivity. And the another one classification the phonon liquid electronic crystals, where we can have all these three properties interlinked way. So there are plenty of materials have been explored to study the thermoelectric performance. It's starting from bismuth telluride to very recently there are tellurium-based materials have been greatly zoned. For example, if you see the data here, so the ZT is over 2.0 to 2. Now 2.3, 2.6 also have been reported in case of tin telluride. So it clearly shows that the commercialization of the thermoelectric materials is really possible. So researchers are looking to find out very alternative materials to achieve high figure of merit. So anyway, so I'll move into my today's talks on the layered materials. If you look into the literature, like very recently, people have started thinking about the layered materials for thermoelectrics. Why? Because these layered materials have the place to have more amount of scattering, as well as we can place the materials what we wanted to have as a token or nano inclusions. So thereby we can increase the ZT. So if you look at the thermoelectric material selections in the in the periodic elements, so if you look at the dopants, there are plenty are available. Again, there are that we need to decide either one should lower the thermal conductivity and we should enhance the electrical conductivity. So in our group, so we are concentrating on these following materials as all falls on the layered materials category. For example, SNSE. The SNSE is an well-known material, and it has been explored for well, like a couple of years, and it has the anisotropy in the crystal structures, as well as the quite good band gap will give you the range of mid-temperature range to high end, and then unharmonicity. This lattice unharmonicity will give you the low thermal conductivity. And then if you look at the another well-known material, that molybdenum disulfide in the layer structures, it will also have the van der Waals gaps. So these gaps can be filled by many kind of layers or whatever, like the dopants can be filled into that. And then the tunable band gap makes us to explore this material for different temperature range. And then Valley degeneracy, this also makes us to understand the crystal structures as well as the band gap tuning. And if you look at the BA to SE3, this is also one of the most well-known topological insulator, and this quantifiable layer makes and van der Waals interactions. This all makes this material is more viable for thermoelectrics. And the another one is the bismuth telluride, which is well explored for thermoelectrics. It has that lone pair electrons as well as the coordination factor. It depends upon the temperature and changes the lattice shrinkage or lattice sizes. So this makes more informative as well as interesting to do the thermoelectric studies. So again, these all have to contribute for the contribution of the enhancement of ZT. So let me move into first start with the MOS2 layered nanostructures. So here in this particular work, we have done the polyaniline. It's a well-known material which has the good electrical conductivity. So we are incorporating into the MOS2 lattice. So where we would able to observe some significant changes in the thermoelectric performance. So these are all the experimental procedure, but I will not go into detail. So we have prepared different weight percentage of PANI, like start with 0.5%, 2.5%, and up to 10%. So these are all the images of the pellets what we have made using that PANI incorporated MOS2. Here we can see that it's clearly revealed that MOS2 PANI incorporation is highly observed. And the both things have been observed in the Raman as well as the XRD also. So it clearly tells us that the PANI is incorporated into MOS2. So if you look at the elemental mapping using the SEM, so here we have clearly seen that this contribute the distribution of nitrogen carbon in the MOS2 matrix. So here the material is highly incorporated into MOS2. So this is the HRTM as well as the XPS analysis to find out the interaction with the different weight percentage of PANI into MOS2. Here we can correlate that this particular interaction of 5 percentage of PANI gives us the signal of nitrogen. So here we can see that this MOS has the very good interaction with the PANI. So this is the main area of our focus. So here we have very good results about the Seebeck coefficient as well as the Hall measurement. Here we have clearly observed that the Seebeck coefficient enhancement is observed at 5% of PANI. This is really interesting because this is the first report on PANI incorporated into MOS2. So here we are able to see the particular layered structures will give us the high Seebeck coefficient at the temperature range of 400 to 500. So this significant results gave us an interesting factor that this even the electrical conductivity also increased by having the 5-8% of PANI. That, and also we have achieved the maximum Seebeck coefficient of 105 microvolt per Kelvin. And if you look at the thermal conductivity data is very important to have the to determine the ZT of the material. For example, here, if you look at the data, the pure has the value of the pristine is 0.3. But when we go for 0.5, there is increment in the thermal conductivity. However, when we go for 0.5 and 10 weight percentage, almost we could able to get the very good lowering the thermal conductivity. So the optimum amount of PANI gives us the excellent Seebeck coefficient as well as the thermal conductivity. So that we have calculated the ZT. The ZT is it's good, really good in terms of when we go for the MOS2 PANI matrix. So here we could able to get the order of 0.005. So this is one of the important results in terms of PANI MOS2. So in the next work, we have done the incorporation of MOO3 into the MOS2. So this we have intentionally done because of the layered structure of both MOS2 and MOO3. Here the MOO3 is not like exactly the layered structures, but it has the very good crystal structures. So these kind of crystals can you like one can make the possibility to have the more scattering in case of phonon scattering. This is the XRD pattern. XRD patterns were confirmed to the formation of both MOS2 and MOO3, and the same was observed in the Raman as well as this XPS. So I will not go into much interaction about this like Raman as well as the XPS. However, we can see the very clear interface effect in the TEM, where we could able to find out the MOS as in the layer structures, whereas the MOO3 as the like broad kind of structures or some kind of plate-like structures. So these structures are greatly contributing for the enhancement of ZT by means of having the low thermal conductivity. So here, this is a very crystal clear structures about the layered structure of MOS2. Here you can see that we have the multiple places for the scattering. If you look at the image very clearly, you can see that plenty of places where we can have more amount of scattering. At the same time, these MOO3 nanorods are connecting these MOS2 layers to have more Seebeck coefficient. So here we have correlated the results with the unharmonicity as well as the interface phonon scattering. So we can have clearly the idea of how this MOO3 is distorting the MOS2. So one can say that this the interaction is very weak, but it is not the case. But in case of the unharmonicity, the MOO3 interaction with the MOS2 gives us the ultra low thermal conductivity. Thereby, we have a very good ZT of around 1.2 for the particular concentration of S2 sample. And this particular work we have very recently published, and this is available in the web page. And the next work, what we have done is that, so as I already mentioned, there is the composites and the doping. In composites, we can have the lower amount of thermal conductivity. However, the electrical conductivity, we are not very sure. But when you go for the doping or nano inclusions, in these cases, we can have very clear information about how the electrical conductivity enhanced when you go for the doping. As well as the thermal conductivity is lowered when you go for nano inclusions. So the both things have been very clearly observed in these studies. If you look at the data of like thermoelectrics, we can see that the Seebeck coefficient is significantly like enhanced. For example, in the case of MC5 samples, here the 5% of copper gave us a very good Seebeck value in the range of 360. Around 360 Kelvin. So this clearly tells that the doping is important to enhance the Seebeck coefficient as well as the electrical conductivity. So by having the nickel as a dopant in the MOS2, this also gave us the lower thermal conductivity for the particular concentration of around 7.5 and then 10% of nickel. So in both cases, the copper as well as nickel cases, the lower thermal conductivity also observed. And the next very good, interesting layered material is the tin selenide. In the tin selenide, the reported GT is now over 1.6. It's a well exposed material for thermoelectrics. So we have made some interesting effect by having the indium mesh nano inclusions. So this is external procedure. We have started this by vacuum sealing method, and then we have done the melting, as well as after that we have collected the samples and we have done the ball milling. Then the ball milled samples have been taken to the spark plasma sintering for tensification, where we would able to see exactly the grains can be seen with the indium nano inclusions. So this is a very interesting study because it's not easy to have this indium into the SNSE layered matrix. If you look at the boundaries of each like SNSE as well as tin, indium. So in the case of the higher concentration, we can able to clearly see the size of indium close to 5 nanometer. And this we have observed clearly by the EPMA data. EPMA data very clearly reveals that these indiums are precipitated on the surface of the SNSE matrix. So these places are very, very important to have the scattering effect. If you go for higher concentration of indium, in more places we can able to see the indium as nano inclusions. So this similar trend was clearly observed in the thermal conductivity. For example, if you look at the data, that this is the pure SNSE, where it closes to 0.8 to 0.8 to 9.95. Whereas if you go for higher concentrations, like a higher amount of indium, we can lower the thermal conductivity by almost 50%. So this is a very interesting result. And the another work we have tried with the like antimony incorporation into SNSE layer structures. Here also we can able to see that this antimony is highly incorporated into the matrix of the SNSE. Whereas here also we have very clear contribution of this antimony as a scattering center, where we have lowered the thermal conductivity by over almost more than 40%. And in another word, the MN is a very important material. So where we have used this MN to dope with the SNSE. In this case also, the quite close that 0.5 and 0.3 have given very low thermal conductivity. So, and we have observed the similar like the incorporation of MN in the matrix by HRTEM. And another interesting work by the germanium. Germanium also, the best thermoelectric material. So here we have incorporated this germanium into SNSE. So here we can able to see that the germanium particular concentration lower the thermal conductivity. Here we can see that what the 1% of germanium gives us the low thermal conductivity compared to the pristine SNSE. And here now I'm moving to the bismuth chalcogenides. The bismuth chalcogenides, the bismuth selenium as well as the tellurium. In case of bismuth selenide, it's a well known layered material structure. So here, why we are going for bismuth selenide is it's also topological insulator. So here it has the good Seebeck coefficient, and also it can be obtained high ZT at room temperature. So by having the SP doped BA to SE3, we have lowered the thermal conductivity compared to the reported work very recently. So this is one of the first report in kind of antimony doped BA to SE3, where we have lowered much close to close to 0.25. So this clearly tells us that antimony significantly lower thermal conductivity. And in the last part, I will cover, like, we have made some effort into make the BA2TE3 on wearable thermal generator. For example, on carbon cloth as well as the nickel copper cloth. So here are some interesting results. Like in terms of carbon cloth as well as the copper cloth, so we would able to see that the materials are highly coated on the surface of the cloth. So this clearly tells that this cotton fabric as well as the nickel CU fabrics are having highly uniformly coated BA2TE3, and we have tested for the Seebeck coefficient as well as mobility and then conductivity, and we have called it the power factor. The power factor for PCCF and VN quite similar, but that BCNCF, that is the nickel nickel copper fabric has given the very good power factor. And also we have taken this to fabricate the sensor like that. This is the one which we have developed in our laboratory. This wearable sensors, the thermal generator, gave us a very good value of, for example, this we have checked with the different persons. The temperature is 27 degrees C. However, it depends upon the person's body temperature. So we could able to demonstrate that this device can clearly sense the body heat, as well as it could transform the output voltage of around 0.042 millivolt using this the wearable thermaltic generator. And we have also reported this data very recently, and it is accepted. So let me summarize what is our contribution to these layered nanostructures. For example, in case of MS2, we have done like very good amount of work in the case of copper as well as the nickel. So here I have summarized that lattice thermal conductivity is greatly lowered here, and then this is due to the unharmonicity as well as the layered structures. And the second one, this is the doped MOS2. Here also we have significantly lower thermal conductivity. So our strategy is successfully convinced that this layered structures can be tuned for lowering structures by having the nano composites as well as the nano inclusions and dopants. If you look at the data of this BH2TE3 for wearable sensors, it greatly has the impact by when you apply very different kind of temperatures gradient. So this is our research group. Like we are a very big group of people, and this the whatever I have given here as a presentation, this was done by like Ms. Abhinaya, Kavirajan, Dona, Shalini, Vijay, Monica, and Janisha. And I thank our collaborator as well as funding support to execute this work. Thank you.
Great. Thank you very much for your very nice talk. So do we have any questions? I don't, if you have any questions, please don't hesitate to type on the chat. Right, perhaps I can start one. I don't know much about thermoelectrics, but is there a scope for, I mean, of course, the Holy Grail will be to have a single material that combines everything, yeah? But yes, is it a scope for hierarchical structures that can assemble all the way from nano structure to macroscopic scales that can deliver improved performance?
Exactly. But that is not easy, right? So yeah, if you can have that hierarchical structures with the different kind of materials, if you can like either by manipulating by different techniques, so that is great thing. But it's not. I don't think it is easy.
Yeah. I'm saying this because it's interesting developments on the ability to process a number of materials using scalable techniques from solution, for instance, at a very low dimension. So in principle, one can, we're adopting similar approaches for creating hybrid, for instance, super lattices, a very large scale.
Yes.
And nanometer or sub-nanometer resolution in terms of thicknesses. And I was wondering whether similar techniques can be also exploited for thermoelectrics. I've been looking around, but I haven't seen a lot on that area.
Yeah.
Technology has been advancing, but I think there is a lot of ideas that can be tested.
Yes.
Yeah. Right. That's good. We still have time for a few questions. Any question from anyone? Then I think we will stop here. Thank you, Professor Mani, again for the very nice talk. And
thank
we'll
you,
move
Professor Thomas.
To the next contributed talks. Thank you.
Thank you.
Yes, Professor Thomas, we may start the contributory lecture.
Yeah, we will start because we still have a few minutes before,
yes,
but we can start. Okay, great.
Yes,
all right, I think the next contributed talks, that we have 3 in this session. So it's 10 minutes in total. There will be a bell at the 6th minute, and then a second bell at the 8th minute. So make sure everybody keeps on time. And then we have a few minutes for questions. All right. Great. The first contributory lecture is from Dr. or Mr. Salini. I'm not sure who is the speaker. And the title of the talk is Nickel Decorated Layers of Molybdenum Disulfide Nanosheets for Flexible Energy Harvesting Applications. If the speaker can share the screen, and we can start. Great. Yeah, we can see the screen nicely.
So can I start?
Oh, yes, please. Please go ahead. You have 8 minutes.
Okay, sir. Like myself, Shalini, I'm working on variable thermoelectric generators in nickel-doped MOS2 nanosheets for flexible energy harvesting under the guidance of Professor Ikeda, Shizuoka University, and Dr. M. Navneethan, SRM University. Like outline of my talk follows as like background of thermoelectrics, material properties, objective, purpose, experimental procedure, results and discussion, and conclusion. Moving on to the background of thermoelectrics, about 90% of world power is produced by heat engines using fossil fuels. This fossil fuels waste energy cannot meet the demand of fast-growing world. So there is a need of developing any new energy conversion technologies, like such as solar energy, wind energy, etc. But even though the solar energy and wind energy are the new energy conversion technologies, like the efficiency of these materials, like these devices, were very less, and they were used to produce waste heat. So in order to overcome that, the new technology has arisen called as thermoelectrics, where thermoelectrics is a green technology, and it direct conversion of heat differentials into electrical voltage and vice versa. And this thermoelectric voltage works on two effects. One is Seebeck effect as well as Peltier effect. And the thermoelectric efficiency is measured using the formula ZT is equal to S square rho divided by KE by KL, where S is the Seebeck coefficient, L is the electrical conductivity, Ke is the electronic contribution thermal conductivity, and KL is the lattice contribution for thermal conductivity. In this formula, we can see the interdependency of the parameters S, Seebeck coefficient, electrical conductivity, as well as thermal conductivity. For a good thermoelectric material, like we should have low thermal conductivity, high electrical conductivity, as well as high Seebeck coefficient. To achieve that, like we can't even achieve the like high electrical conductivity as well as high Seebeck coefficient, so that we need to optimize the Seebeck coefficient as well as electrical conductivity. For that, semiconducting materials are the best materials with a carrier concentration of 10 to the power of 19 to 21 carrier concentration. Then moving on to the material properties like I'm going with MOS2, where it has good chemical stability and thermal stability with low thermal conductivity, low cost, and the band gap is around 1.2 to 1.9 electron volt. And then that MOS2 will be coated on a flexible substrate, where the flexible substrate here is a carbon fabric, which is a good conducting material, flexible, and it is heat resistant and it has good absorbing properties. Then moving on to the preparation method of MOS2 and nickel doped MOS2. Here, like I have taken 4.5 grams of thiourea, added in 72 ml of DI water, and stirred for 30 minutes. Then I have added 2.5 grams of molybdenum hepta, ammonium hexamolybdenum hepta. Then I have added the nickel source, stirred for 1 hour, and transferred to autoclave and kept at 180 degree for 24 hours, and washed with DI water and dried with ethanol, and annealed 300 degree for 2 hours in an inert atmosphere. After then the material has taken for structural studies, where here the peaks shows that 002, 100, 102 suggests the straight structure of MOS2, and it was well matched with the JCPDS card number 751534, and the peak located at 14.02 with 0.69 nanometer. And there was an like shift in the lower angle side, like plane 002 as a lower angle shift, and 02 plane indicates the periodic sequence of MOS to layers in C-axis, where the mismatch in the ionic radius leads to a lower angle shift, and it confirms the presence of MOS2 matrix. Then further we have went to the Raman analysis, where we found to have E1 2G mode and A1G mode at 382 and 407 centimeter per centimeter, where at 382 it was interlayer displacement of MO and S atoms, and at 407 it was due to out of layer symmetric displacement of S atoms. Then moving on to the morphological analysis, like we have carried out the morphological and found to have a layered structure for all the samples. Then we subjected it to the TEM analysis, where here we have confirmed that the incorporation of nickel in MOS2, where the interplanar distance has been increased with the incorporation of nickel atoms, which includes the MOS2 matrix. Then the thermoelectric analysis has been studied for pure MOS2 and 3 atomic percent MOS2, where it showed 3 atomic percent MOS2 showed the low thermal conductivity compared to pure. It was around 0.2 watt per meter Kelvin at room temperature. Then we have fabricated nickel doped MOS2 variable generator, where the fabric was initially pre-cleaned with soaring process and dried at 90 degree, and then MOS2 has been coated on the fabric at 150 degree, and the coated fabric has been dried at 90 degree, and after that the coated fabric has been fabricated to a flexible TE generator. This is a morphological analysis of the fabricated nickel doped MOS2, where first figure shows the pure fabric, and second 0, 3, 5, 7, 10 shows the coated fabric of nickel doped and pure MOS2 samples, where this shows the successful coating of MOS2 on the fabric. And the summary is like 2H structure of MOS2 and nickel doped MOS2 was prepared, and it was confirmed by XRD, and the morphological of the prepared nickel doped MOS2 was observed as a layered nanosheet by FSM. Vibrational modes have been analyzed by Raman spectroscopy. Elemental composition of prepared sample were confirmed by XPS analysis. Morphological confirms the successful coating of MOS2 and nickel MOS2 on surface of carbon cloth. 0.21 watt per meter Kelvin at room temperature of thermal conductivity was obtained for 3 watt percentage of nickel doped, and this nickel doped was successfully coated on the surface of carbon fabric. And like future work is like I need to take with EPMA analysis, thermoelectric studies, and to fabricate the variable thermoelectric generator. And this is the schematic of fabricated thermoelectric generator. Thank you.
Great, thank you very much for a very nice talk. I don't see any questions in the chat box, but if is there any question from the audience? If you have any question, please do type it in the chat box. Perhaps I have one regarding the use of textiles, for creating this thermoelectric systems. I was wondering whether is there any way that these systems can be embedded with the textiles to form hybrid composites to create the fabric themselves?
No, so like your fabric is the commercial one. Like I'm coating the material on that fabric.
Exactly, but in the future, you could create a nanocomposite that is a functional. The fabric itself is functional. Is there any benefits? If you are coating a material on a fabric, like the properties will be further enhanced, because your carbon fabric is in a conductive material. Like there will be a further enhancement in the conductivity, which that further influences the thermoelectric properties. I see. Yeah. So the degree of decoration plays a role in your generators.
Sorry, Sensei.
The degree of the decoration, how well this material is covered around the fabric.
Yeah, that also makes influence the properties of thermoelectric properties, because like if the fabric has been well coated, maybe the material as well as the fabric properties will be enhanced. If like very less coating, like when we go into further applications of generators, maybe the voltage of the generator will be less compared to a clean coated fabric.
I see. Great. Okay. I see no other questions unless someone has a question would like to ask. Yeah, there is a question. Why the 002 plane is shifted to lower angle? What is the reason? And can you explain about the tensile strength?
This 002 plane has been shifted to a lower angle because the ionic radius of molybdenum is very less compared to nickel. So that is the reason why it has been shifted to lower angle. Like when we come for the tensile strength, like here, like we have not yet calculated the tensile strength of the material.
I see. Great. Okay. In the interest of time, I think I would like to thank once again the speaker, Shalini. Thank you very much for the very nice talk. And we're moving to the next contributory lecture. All right. So our next speaker is Mahesh Jadhav from the Department of Physics and Nanotechnology and SRM Institute of Science and Technology, Tamil Nadu in India. And the title of the talk is Thermal Stability and Thermal Expansion Behavior of Iron, Cobalt, Chromium, Nickel, Aluminum, High Entropy Alloy.
Please others mute your signal. Magis. Yeah.
Okay, Mahesh, thank you very much. We can see your slides. You have 8 minutes for your talk.
Yeah. Yeah. Good evening, everyone. Myself, Mahesh Jadhav. My topic is thermal stability of high entropy FeCO4 NiL high entropy alloy. So basically, this thermal barrier, the application of this high entropy alloy, which I am proposing into the thermal barrier coating, which is applies in the metallic surface, such as a gas turbine or aero engine parts, which is operated at elevated temperature. It allows a reduction in the substrate temperature from 100 degrees centigrade to 300 in 120 micron to 400 micron thickness. Here you can see the gas turbine engine. So the application area is high pressure turbine, where the combustion gases were impacted on the high pressure turbine and which allows to rotate at a higher temperature and produce a higher power. So the structure of a basic thermal barrier coating, here you can see the substrate which is coated on with a bond coat material. That bond coat material should have a chemically homogeneous, and it should form alpha alumina once it's oxidized at a higher temperature, say up to 1100 degrees centigrade. It should have a creep and yield resistant and a low rate of interdiffusion. So what is basically high entropy alloy is it contains 5 elements, at least 5 principal elements, which are having atomic percentage of 5 to 35 atomic weight percent. So due to this high mixing entropy effect, the solid solution formation of FCC and BCC crystal structure will form rather than forming an intermetallic or complex phase during the solidification. It also shows a slow atomic diffusion due to this highly saturated solid solution. And it's very easy to easy process control due to the formation of simple FCC and BCC solid solution phase. But there are different techniques which can be used to make the high entropy alloy, such as arc melting, then powder metallurgy route. So there is a difference in if the same alloy can be prepared by powder metallurgy and arc melting, there will be a difference in the phase formation. So here we have chosen a powder metallurgy route, which is a very convenient way, and we can alter the chemistry of the alloy as per the requirement. So this is the phase formation criteria, which is suggested in the literature. So as I said, this induction melting, casting, powder metallurgy, and sputter techniques can be used to produce the high entropy alloy. So basically, this mechanical activated synthesis is this combination of mechanical milling and followed by the annealing at a high temperature, which produces the high entropy alloy. So there are many literatures which alloys were prepared by using only a mechanical alloying, but producing a high entropy alloy by using mechanical alloying for a longer duration time, it tends to get contaminated due to this tungsten carbide. While milling, we are using a tungsten carbide vials and balls, which tends to get contaminated if you mill for the longer period of a time. There are some widely studied high entropy alloys are ALs, AO, CR, Fe, Ni with change in the aluminum concentration, then with the addition of a copper, then with the addition of titanium. So these are the basic systems which are already studied and well known for their good mechanical properties, structural properties, and corrosion resistance behavior. So basically, this high entropy alloy is having a combined properties like a high strength, high ductility, good oxidation, high thermal stability. And this is a new research field which is having the very interest in the scientific. There is having a increasing scientific interest due to this high temperature. It's due to its application in high temperature turbine blades, high temperature molds and dies, hard coatings on cutting tools, or even a components of a fourth generation nuclear reactor. So I'll go straight towards the results. For that, I have prepared this thermal stable, this FeCOCr NIL high entropy alloy. And as I said, this is going to use in the high temperature gas turbine engine. So the properties required are whatever the alloy we are preparing, that should have a good thermal stability. And the phases which are present at the room temperature, that should be stable up to high temperature. So to study that, this high entropy alloy, we are prepared using a mechanical activated synthesis. That is a mechanical alloying. For this alloy, we are prepared by using 2 hours of mechanical alloying, which is using a ball mill. And then it is made as a pellet and then heat treated at 1100 degrees centigrade to form a complete solid solution formation. And this alloy, we are then hot pressed using hot pressed at 1100 degrees centigrade. And then with the pellet where the small pellet were taken for this in situ high temperature XRD studies. And as we can see at this in situ high temperature XRD pattern shows at a room temperature the presence of FCC plus BCC phase, and which is stable up to 1000 degrees centigrade. And here we can not see any additional phase formation in up to 1000 degrees centigrade, which suggests the thermal stability of the high entropy alloy. And here you can see I have calculated the lattice parameter for this high entropy alloy from room temperature to 1000 degrees centigrade, and we can see the lattice parameter for the FCC and BCC both shift towards the lower 2 theta angle, and the lattice parameter changes from room temperature, it is 3.585 to 1000 degrees centigrade 3.62, as well as for the BCC 2.8 to 2.9. This is because of the increase in the high temperature, and which causes to increase the lattice distance, and the lattice parameter were increased. Here is the BSc micrograph of FeCOCr NIL high entropy alloy, which is hot pressed, and we can see the segregation of the phases, the contrast phases, which can be seen like dark gray, light gray, and the black. This dark gray region where we can see everywhere, which is a chromium rich, and the composition is given here by using EDS analysis and taking an average. And there you can see the light gray phase, which is marked by B, which is belong to FeCOCr NIL, and C, there you can see the black spots, which is belong to the NIL, and there is some porosity also because the density of the sample is 97%. And here to confirm that, as I said, this thermal stability I have not only studied by in situ high temperature XRD. To confirm that there is no phase transition up to 1000 degrees centigrade, I have taken a DSC thermogram, which is up to 1500 degrees centigrade. And here we cannot see any, we can see only a single endothermic peak without any additional phase transition or any additional peak. So you can see here that 1294 is the melting point of the alloy. And further, I have used a dilatometer for thermal expansion measurement. And from the dilatometer study also, we can infer that there is no phase transition, because this thermal expansion measurement device, if any phase transition happens, the thermal expansion or any softening of the alloy, then we cannot see this continuous increase in thermal expansion. If there is a softening in between, then the thermal expansion curve can change. So you can see the continuous increase in the thermal expansion up to 1000 degrees centigrade. Here is this table shows the CTE, which is referred. It's a reference for the TBC system. So nickel-based superalloy is to have thermal expansion at 1000 degrees centigrade is 12 to 17. For the bond coat material, which is suitable, should have 13 to 16 CTE at 1000 degrees centigrade. And here you can see that the thermal expansion at 1000 degrees centigrade lies within the range. So it can be proposed as a bond coat material to replace the macrolide, which is currently used in the gas turbine engine. And I have studied with the oxidation study and found that it produces an alpha alumina TGO layer also. But in this current study, I have not shown this. That is another study we have did, in that we have given that. So the conclusion from this small work is high entropy alloy have been successfully prepared by using mechanical activated synthesis. The phase transition temperature, phase stability at high temperature, and thermal properties were investigated using DSC, in situ high temperature XRD, dilatometry at high temperature. That from the in situ XRD, you can see the formation of FCC and BCC phase, which is at room temperature and stable up to 1000 degrees centigrade without any additional phase formation. DSC analysis also shows no phase transition and only a single melting point, which is observed for the this prepared high entropy alloy, and it substantiates the in situ high temperature XRD results. The thermal expansion curve also shows no softening sudden or any sudden change in the CTE up to 1000 degrees centigrade. There are the acknowledgement. I acknowledge SRM Institute of Science and Technology, Chennai, DST SERV for providing and financial support and helping in the characterization, Surface Engineering Division, National Aerospace Laboratory, Bangalore.
Thank you very much.
Thank you.
Thank you. I would like first to ask the audience if there is any questions.
Hello, Magesh, could you hear me?
Yes, sir.
Yeah, it's a very good talk. It's very nice. It's a high-end applies are very interesting materials. I would like to ask only one question. See,
Yes,
more high-end applies are actually most of the iron, like chromium, nickel-based alloys, right?
Yes.
This and all actually it will get easily oxidized. So, what is the phenomena behind actually this high entropy alloys are high oxidation resistant materials? This is my first question.
Okay.
Second one, actually in our coefficient of thermal expansion.
Yeah.
After 600 degrees centigrade, there is your slope is actually getting deviated, right?
Yes, yes.
So what makes, which material is actually responsible for this change in slope?
Okay. Yeah. So basically, this high entropy alloy, this FeCO-CrNiL, there are a number of studies, and the oxidation behavior, which is also depends on its preparation route, because if the same alloy, which is prepared only by powder metallurgy route, like a mechanical alloying, if you do the mechanical alloying for 10 hours or 50 hours, you will get the complete solid solution high entropy alloy. And if you do the hot pressing of that alloy and study the oxidation behavior, you will not get the same as what I have did in the mechanical activated synthesis. So what I have did here is to reduce the contamination, I have did only 2 hours of milling. There the solid solution formation was not completed, and that alloy I have annealed at 1100 degrees centigrade. So here I have reduced the contamination and as well as the formation of oxides, any other oxide, and that is completely done under the argon atmosphere. So there is no any additional phase also as well as oxides. So after that, that hot pressed sample, and to confirm that, here we can see this DSC also as well as in situ XRD, the formation up to 1000 degrees centigrade, there is no additional phase formation. from with other than the FCC and BCC. And the same alloy, here I have not shown that study. I have did the oxidation study up to 300 hours at 1050 degrees centigrade, and it is sustained up to 300 degrees centigrade, and it is still having the capability to go beyond that. But due to the experimental time and constraint, I have did up to 300 hours and have observed the TGO, that is the oxide thickness layer. It is 6 micron. So the mostly this gas turbine, the critical TGO layer thickness is 7 micron. So I have stopped at 6 micron up to 300 hours. So I have did the cyclic oxidation studies as well. That is in the process. So that characterization is in the process.
Good. Okay, Manish. Okay, good.
Maybe there is one more question from the audience that if you could address like in a very quickly is how could you avoid a corrosion in the presence of iron in your HEA material?
So basically, I have focused my studies on the high temperature oxidation, and I have not studied based on the corrosion, but there is a literature which is having studied this like corrosion properties as well, but I have not gone through the corrosion behavior and I have not studied yet.
Okay, great. Thank you very much once again. Thank you for
thank you
very
so
nice
much.
talk. Thank you. So, and I think we're moving now to the third contributed talk and the last for this session. The talk is by Asina S. from research scholar, Department for ECE, Government Engineering College, Barton Hill, Trivandrum, Kerala in India. And the talk title is Simulation-Based Investigation on the Performance of Metal Oxides as Charge Transport Layers in Lead-Tin Perovskite Solar Cells using the SCAPS 1D. I guess that refers to software. So Asina, if you're there, if you can share your screen.
Hello. Yes, Asina, please unmute your audio.
Right, we can see your screen.
Good evening to all.
Hello.
I hope I am audible.
Yes, you are audible.
You have 8 minutes, Asina. Please go ahead.
I am Asina from Government Engineering College, Barton Hill, and I'm here to share some of my views on simulation-based investigation on the performance of metal oxides as charge transport layers in lead or tin perovskite solar cells using SCAPS 1D. As an introduction about the perovskite solar cells, they are the emerging solar cell technology that have replaced the dye-sensitized solar cells. And during a decade, there have been a rapid increase in the efficiency from 3.8% to 23% in 2019. The main criteria of this perovskite solar cells are they uses organometal halide perovskites as the absorbent materials. Mainly, or the commonly used perovskites are methyl ammonium lead halides or methyl ammonium tin halides. This is the basic structure of the perovskite solar cell that is used for the simulation here. That is the basic planar NIP structure, which is having a whole transport material. For the basic structure, we all uses the spiro, that is the solid state whole transport material, and the perovskites are the lead or the tin-based perovskites, and the ETM layer is the titanium dioxide. And the proposed structure, I would like to introduce ZNO as the ETM. It is another most reliable material that can replace titanium dioxide. And there are many research going on in this case as well. And it has the material characteristics similar to that of titanium dioxide, and it has higher electron mobility than titanium dioxide. And it enables use with flexible substrates and does not break your any high annealing temperatures. And about the HTM layers, instead of the solid state HTMs and organic HTMs, we go for the metal oxide HTMs, that is cuprous oxide, copper oxide, and nickel oxide. It is a comparative study in the simulation to know how it affects the performance of the cell. For the evaluation, we use the SCAP software. SCAPS, it is the solar capacitance simulator software, and different parameters for each of the layers of the perovskite solar cells are used here. And in this case, I have changed some of the key parameters or varied some of the key parameters of the ETM section. That means the electron transport material, the energy band gap, and electron affinity are varied to study how it affected the efficiency or the performance of the cell. And later for the absorber layers for both the tin-based and for the lead-based perovskites, the acceptor concentrations and the doping, the acceptor doping as well as the trap layer concentrations are varied. And the performance of the isodeno-based perovskite solar cells is evaluated using 3 different metal oxides, that is cuprous oxide, copper oxide, and nickel oxide. These are the material parameters that has been used for this CAP simulation. And the varying parameters are band gap, affinity, Na, that is acceptor doping, and Nt, that is the trap defect density. Optimization of the band gap of ETM. Whenever I change the band gap, I could see that it doesn't affect the efficiency of both the solar cells in a very good manner or greatly. It always remained, it must remain stable. And for optimization of electron affinity, when the electron affinity was changed from 4 to 4.4, there was a decrease in the efficiency for both the solar cells. And this electron affinity and band gap, they mainly affects the conduction band offsets of the cell, offsets of the layer. And the conduction band offsets are in cross relation with the next layer, that is the perovskite layer. Whenever there is an electron transport for this from the perovskite layer to the electron transport material, the band alignment should be satisfying. Then the optimization of the Na and Nt of the absorber layer. Whenever we are increasing the acceptor density, we can see that the efficiency slightly increases. But for lead perovskite, it is better to use the intrinsic mode of doping itself. But if we are increasing the Na beyond a limit, it will go for auger recombinations, and it can reduce the it can cause other reduction in the current as well. And for NT, whenever there is an increase in the trap density, it can also result in recombination rates, and it can affect the efficiency. This is the same case for the tin-based perovskite as well. But for the tin-based perovskite, it's better to dope for a p-type doping, because the tin perovskites are having a self-doping property, or the SN2 plus ions are formed by the oxidation of SN2 plus occurs, and it can affect the efficiency as well, or it can affect the degradation of the perovskite solar cells. So it's better to improve or increase the doping level of acceptor doping in case of a tin-based perovskite. Thus, the optimized values are energy band gap of about 3.3 and 4 is the affinity. And for defect density, it's almost the same for both the perovskite layers. And the acceptor concentration is, we are giving a p-type concentration or increase the p-type doping for a tin-based layer. These are the results for different HTM layers used. And as per the result analysis, we could see that the cuprous oxide gave a better efficiency than other metal oxides. And it's better to use the cuprous oxide as the HTM layer. And we can hope for better efficiency as well in the perovskite solar cells. That's all. Thank you.
Thank you very much for your talk. So do we have any question from the audience I would like to ask the speaker? Any questions? I have a few questions from my side.
Yes,
why your model and simulations failed to capture the higher efficiencies have been achieved for certain perovskite, the lead, for example, based perovskite, or is this state of the art for this particular composition?
For lead perovskite, as compared to the tin perovskites, when we are going for the material parameters, we can see that it has better band alignment with isodono, or that means the ETM layer, as well as with the cuprous oxide. That means for the ETM layers, the conduction band offsets or the conduction band minimum and the valence band maximum should be lower than that of the perovskite layer, and it very well satisfies with the lead perovskite as compared to the tin perovskites. And also in the case of other metal oxides, as the HTM layer, the well satisfying valence band maximum comes for the cuprous oxide.
I see. Do you do any validation of your calculations with a real experimental data to compare? I mean, how important these parameters are?
No, sir, I haven't gone for it, but I am looking for the experimental validations.
I see. Okay, great, thank you. Any other questions maybe someone would like to ask from the audience?
Yes, Hasina, are you studied any stability measurement? Because perovskite.
But in perovskite, it's the common disadvantage is the stability and degradation problems. But I have only gone through the literature surveys and the simulations, and based on that, I could see that the tin perovskites are have more degradation issues. That means in tin perovskites, there are chances of oxidation issues by forming of Zn2 plus or Zn4 plus ions. This further degrades the perovskite layer and affects the efficiency. And in later, there were many works coming as the oxidation. In order to avoid or limit the oxidation layers of the tin perovskites, we can code the SNF2 layers to reduce the degradation rates and all. And in case of lead perovskite, one of the major disadvantage is the toxicity of the lead. That is why most of the studies then went to other perovskite materials. Now I have concentrated only on the simulation parameters now, and I have to go for the stability as well as other experimental validations.
Okay, good.
Great. I think this is the end of our sessions. Thank you all for attending and presenting your work on.
Yes. Also, I thank to invited speaker Navanithan and the contributory lecturer. And also a special thanks to chairperson Professor Thomas on behalf of our organizing committee ICON 2021. So the next section will continue in the same platform. So you may wait within 1 or 2 minutes, it will continue.
Great. So, yes. Bye-bye everyone.
Mm-hmm. Hello all. So we can just continue with actually 5th section, which is manipulation of manipulation and characterization of materials as a nanoscale and atomic scale. So here we have actually Professor L. Sudha, Professor and Head of the Physics and Material Science Department, SRMIST Ramapuram, to take over the session as a chair. She is extensively working on the nanomaterials, dielectrics, and crystallography, and so on. Professor L. Sudha, madam, can you please take care of?
Thank you, Dr. Suresh Perumal.
Thank you.
Just a minute. Good evening, all.
Good evening, ma'am.
Yeah, good evening.
Yes.
Can you see the screen?
Yes, ma'am. We could see.
Yeah. Good evening, everyone. I take privilege in chairing this session on manipulation and characterization of materials at nanoscale and atomic scale. And this is session 5F of International Conference on Nanoscience and Nanotechnology organized by Department of Physics, SRMIST Katanglatur. And I take privilege in welcoming the contributory lecture presenters and invited talk presenter, Professor Michael Short. And invited lecture is at 6:20 IST. And the remaining lectures, first lecture is CL94. And the guidelines for presentation is contributory lecture is for 10 minutes and 8 minutes for presentation and 2 minutes for discussion and interactions. So can I call Dr. Tripati Patri to present his lecture on temperature dependent X-ray diffraction and dielectric spectroscopy studies on dysprosium ion substituted 4-layer.
Tripati. Mr. Tripati, are you there?
Tripati Patri, can you hear me? Abstract number 685, CL94, contributory lecture 94.
It seems he's not here. Can we
Okay.
go with the next speaker?
Yeah.
Then again.
And CL95, abstract number 761, investigation of Dr. Sumitra Nangotamban.
Yes, ma'am. Good evening, ma'am.
Yeah, good evening. She's going to present on investigation of Raman signature with interface properties of gallium nitride decorated reduced graphene oxide nanocomposites.
Thank you,
Sumitra?
ma'am. Can I share my slide now?
Yeah.
Thank you.
So 8 minutes for presentation.
Is it visible now, ma'am?
Yes.
So, good evening, everyone. I'm Sumitra Nongtombam, a PhD student working under the supervision of Dr. Bibu Prasad Swain at National Institute of Technology, Manipur, India. So today I'm going to present on the topic investigation of Raman signatures with interface properties of gallium nitride decorated reduced graphene oxide nanocomposites. Here are my outlines. So to introduce with graphene as an imperative material owing to its unique superlative properties in charge conduction, high thermal and mechanical strength, glass surface area, and so on. And I've presented in this figure the difference in structures between graphene oxide, and reduced graphene oxide. And also in the recent years, graphene has been made hybrids with other functional semiconductors as it offers flexibility, functionality, and novelty, thus making it a prospective material for a wide range of applications, including energy storage devices and conversions, chemical sensors, nano generators, and biological applications, and so on. Meanwhile, Group 3 nitride-based semiconductors mark potential as the basis of new generation optoelectronic and also superior characteristic in terms of voltage, temperature, power, and frequency devices. Gallium nitride among these Group 3 nitrides is fascinated because of its wide direct band gap of around 3.4 electron volt, attracting vast research in the field of nanoscience and nanotechnology with its important properties including chemical stability, high carrier mobility, excellent electrical properties, and high electrical breakdown field. Utilizable in various applications such as UV detectors, LEDs, photovoltaics, gas sensors, etc. So in this work, we're going to synthesize the reduced graphene oxide, gallium nitride, nanocomposites using a single-step chemical reduction route, which itself is a new approach. And so we are just motivated to investigate the surface characteristic of gallium nitride when embedded in the RGO network. The objective of my work is to initially prepare graphene oxide by modified Hammer's method, then to synthesize reduced graphene oxide gallium nitride nanocomposites with different weight percentage of gallium nitride, then to study the different properties of RGO gallium nitride nanocomposites. A scheme is shown for the preparation of RGO gallium nitride nanocomposites, where initially graphene oxide is prepared using a modified Hammer's method, using the graphite powder and sodium nitride powder as the precursor metals. Then the as prepared graphene oxide is dispersed in DI water and then stirred using a matic stirrer at room temperature. Then after around an hour, gallium nitride powder will be added after it was observed to be properly dispersed. Then after some time, then hydrogen hydrate will be added, which is a standard reducing agent, and then we increase the temperature of the reaction product to about 90 degrees centigrade, and left for around 2 hours to obtain our desired reduced graphene oxide gallium nitride nanocomposite. And these are the various characterization techniques that I have used in this work to analyze the properties of RGO gallium nitride nanocomposites. And here this slide shows the same images of RGO gallium nitride nanocomposites, varying the weight percentage of gallium nitride from 1% to 20%. And we see from the same images that the nanocomposites show irregular, twisted, and crumpled morphology, over which spherically shaped gallium nitride nanoparticles are distributed unevenly over the RGO sheets, and the formation of gallium nitride nanoparticles are more clearly visible in the 20% weight of the gallium nitride. And the average particle size were found to be decreased with the increase in concentration of gallium nitride, and it was calculated within the range between 370 to 180 nanometer for gallium nitride nanoparticles. And this slide shows the XRD spectra of RGO gallium nitride nanocomposites, and this clearly shows the exhibition of both the gallium nitride planes and RGO phases, which is presented in the table, all the different diffraction planes and the various planes of gallium nitride. These are attributed to the hexagonal wordjet structure. And we also observed that the crystallinity of the nanocomposite increases with the increase in concentration of gallium nitride, and the crystallized size were calculated, uh, and it's found to be increased from 26.1 to 31.5 nanometer, while increasing the weight percentage of gallium nitride. And we saw the FTR results of the RGO gallium nitride nanocomposites, and shows the presence of different functional groups of attached to the nanocomposite found at the different vibrational frequencies. And photolumination spectra for the room temperature are shown in this slide. And the left side of the profile shows the PL spectra, which clearly shows the observance of the near band edge emission, with this maximum emission wavelength at 3.13 electron volt. And the right side of the profile shows the observance of blue luminations in the spectral range 2.57 to 2.72 electron volt. And here we show the Raman spectra of RGO gallium nitride nanocomposites, which presents D band, G band due to the first order scattering of the RGO and a broad peak due to the corresponding to the 2D band and D plus G band respectively. And here D band results from the presence of vacancies or dislocations in the graphene layer, and which is identified as defect band, and G band is due to the in-plane vibration of sp2 hybridized carbon atoms, which is identified as the tangential band. And this first order peak of the RGO is deconvoluted into 5 peaks, where 3 additional peaks are observed in a deconvoluted peaks. And here from this spectra we observe that the position of the D band is shifting into the lower frequency side while increasing the concentration of gallium nitride. And this shows that the less structural defects were detected with more content of the gallium nitride in the nanocomposite. Uh, Moreover, we have also calculated the intensity ratio of D band, G band, where it was found to be decreased from 2.40 to 2.21 while increasing the concentration of gallium nitride. This shows that less structural defects were detected with more association of gallium nitride nanoparticles in the RGO network. And also the second order peak for RGO was deconvoluted into 4 peaks, and here we see that the width of the 2D peak is found to be decreasing from 1% to 20%, and this implies that the number of graphene layers decreases with the increase of concentration of gallium nitride. So the reason is due to the less stacking of graphene sheets with more incorporation of gallium nitride nanoparticles in the RGO network. And this shows the Raman spectra in the range 500 to 750 centimeter in bursts for the 20% weight of
Sumitra,
gallium
you have
nitride.
another 1 minute.
Yes, sir. Only one slide. Thank you. And we have observed a redshift of 6.63 centimeter in bursts in the E2 high mode of gallium nitride, and this observance of redshift postulated that the stress present due to the gallium nitride in RGO network is tensile. So to conclude that we have successfully prepared reduced graphene oxide gallium nitride nanocomposite with a simple chemical reduction route, and we observed that with more association of gallium nitride nanoparticles, crystallinity of the nanocomposite were also increased, and also the this intensity ratio decreasing. This indicates the less structural defects were detected with more association of gallium nitride nanoparticles and so on. And so this from this we conclude that as we study the surface study, we can applications can be extended to energy storage devices and so on, as the surface study is very important in understanding the absorption size, transfer process, and conduction mechanism and so on. Here are my references. Acknowledgement. Thank you. Thank you all.
Thank you, Dr. Sumitra.
Thank you, ma'am.
Yeah,
Thank you very much.
you're from NIT Manipur.
Yes, ma'am, from NIT
Yeah.
Manipur.
Yeah, it's a good presentation. Any
Thank you,
questions? Any questions from the audience?
So Sumitra, it was a very good presentation.
Thank you, sir.
Just I would like to ask one question. So
Yes, sir.
what makes it, because you have shown that your crystallinity of your material when
Yes, sir.
RGO content increases, it increases, you are saying. So why so?
Pardon, sir?
The crystallinity of your material increases when you
yes,
increase the RGO content, right? So why it's so? Why this crystallinity increases? Is there any answer for it?
With more this association of gallium nitride nanoparticles, this staking of graphene sheets are also decreased, and this association of gallium nitride nanoparticles are more with the RGO sheets.
Okay. 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 Fine. Thank you. Thank you so much.
Sir.
Anyone is there to ask questions? Okay. So if there is no more question, thank you, Sumitra.
Thank you, ma'am. Okay.
Yeah.
Thank you.
Yeah. Next, I would like to call Tirupati Patri. Tirupati Patri from Rajiv Gandhi University of Knowledge Technologies, RK Valley. Tirupati Patri, are you here? Can you hear me? Unmute yourself.
Yeah.
Your mic is muted. Yes. Tirupati Patri?
Yes, madam.
Yeah, you can present now. He is going to present on temperature dependent X-ray diffraction and dielectric spectroscopy studies on dysprosium ion, substituted 4-layer barium bismuth titanate Orville ceramic. Yes, you can start your presentation. 10 minutes. It is for contributory lecture, 10 minutes and 8 minutes for presentation, 2 minutes for discussion. Can you please share your screen?
Some problem with the system, madam.
Yeah. Please make it faster. Open your PPT, then you share.
PPT is not visible, madam.
Huh?
Where to get this option PPT?
Yes, sir.
Where will we get? It is on the desktop.
You open your PPT.
Okay.
You open your PPT, then you go to Zoom. In the Zoom app at the bottom, share screen, green colored option will be there. You have to click.
Okay, madam.
You open the PPT.
Yes, I open, madam.
Okay, then go to Zoom. You are in Zoom, right?
Yes, madam. Zoom.
At the bottom, there is a green color icon is there, share screen. At the bottom of the window, Zoom. Green color icon, share screen. It is written share screen. Next to chat box.
Suppose it is getting late, we can go to next one and then come back to.
Okay.
Is it fine? Pratik, can you please wait at least some more time and then find out the see in the screen by down you will see some option called share screen. You should click that and then share your PPT. All right. So just look at it and then we'll go for actually another talk and come back.
So next talk by Mohammad Salman Siddiq. He is from Department of Physics, IIT Mumbai, Powai. He is going to present on photoresistive switching behavior of molybdenum disulfide heterostructure thin films for optothermistor applications. Optomemristor applications. Mohammad Salman. Mohammad Salman, are you here?
Mohammad, are you there? Mohammad? Mohammad, unmute yourself. I think your mic is muted.
Where is?
It's available, ma'am. Was here.
Hello, sir.
Yeah, good.
Yes.
I could hear you.
Actually, I was not allowed to unmute me. That's why there's a problem. Sorry, sir. I'm going to share my screen, sir.
Yes.
Yes. Yes, we could see your screen, Mohammad. You can go on.
Hello, everyone. Myself, Mohammad Salman Siddiqui, and I am a PhD scholar in the Department of Physics, IIT Bombay. And today I am going to present here. The title of the presentation is the photoresistive switching behavior of WO3 MOS2 heterostructure thin films for optomemristor applications. And the outline of the presentation are, first we have deposited the WO3 MOS2 thin films using the thermal evaporation technique. After then we have characterized those deposited thin films using several characterization tools such as Raman spectroscopy, optical microscopy, and the SEM characterization, as well as through the AFM. After then we have done the fabrication of the memristor devices with the FTO as the bottom electrode and the silver as a top electrode, and in the middle the WO3 and the WO3 MOS2 is used. After then we have done the current voltage characterization of the both type of devices, such as FTO WO3AG and FTO WO3 MOS2 AG device. And I will end the presentation with the conclusion remarks. This is the synthesis which we have done using the thermal evaporator technique. WO3 thin films with thickness of around 100 nanometer were deposited using this technique on the FTO coated glass substrate with a growth rate of 0.5 angstrom per second. The basic pressure of the chamber was around 1 into 10 to the power minus 5 millibar. For the purpose of thin film preparation, we have used 15 mg of WO3 powder as well as MOS2 powder in the molybdenum boards for the evaporation. Initially, we have deposited the WO3 thin films. After then, we have used those WO3 deposited thin film substrate for the deposition of the MOS2 thin films to fabricate the heterostructure type of devices. After then, we have deposited the silver as a top electrode with a thickness of around 200 nanometer and a diameter of 1 mm using the aluminum mask to prepare the final device. This is the AFM characterization of WO3 and WO3 MOS2 device. This is the 2D FM image of the WO3 films, and this is the 2D FM image of the WO3 MOS2 films. The roughness of the RMS RQ value for the WO3 layers and the WO3 MOS2 layer is found to be 3.46 and 6.83 nanometer respectively for both the films. And these are the corresponding 3D FM images of both type of films. After then, we have done the surface morphology characterization using the SEM and the optical macroscopy tools. So this A and B are the SEM and the optical images of the WO3 thin films on the FTO substrate, and these are the corresponding optical and the SEM images of the WO3 MOS2 thin films on the FTO substrate. The SEM and the optical macroscopy images reveal that the films are completely covered with a uniform and the grain-like morphology. This is the Raman characterization of the WO3 MOS2 composite thin films. These two peaks, 283 and the 388, correspond to the bending vibration mode of oxygen, tungsten, and oxygen in the monoclinic phase of WO3. And these 726 and 818 correspond to the stretching vibrations of oxygen, tungsten, and the oxygen bond. The peaks below 200 correspond to the lattice vibration of the crystalline WO3, and these two peaks correspond to the A1 2G and A1G mode of the MOS2 films, which represent the in plane and the out of plane vibrations of the sulfur atom within the SMOS layer. And after then, we have done the X-ray photoelectron spectroscopy characterization of the WO3 MOS2 films. A well-resolved doublet is observed at binding energy of 36 and 38.5 electron volt, which correspond to the 4f7 by 2 and 4f5 by 2 for the tungsten, and a peak at 42.1 is also observed, which correspond to the 5p3 by 2. And in case of oxygen, we have observed two peaks at oxygen 531 and oxygen 532. And there the oxygen 531 correspond to the typical bonding of the oxygen atom to the tungsten atoms, and the peaks at O532 is correspond to the surface contamination, that is OH groups. For the MOS2 film, the MO3D spectrum represent two peaks, which are centered at 229.5 and 232.3, which correspond to the 3D 5 by 2 and 3D 3 by 2 components of the MOS2. And for the sulfur also, we obtained the doublet correspond to the 2p 3 by 2 and 2p half component of MOS2. These obtained XPS result confirm the presence of the semiconducting phase of the MOS2 structure. This is the device structure after the depositions of the silver as a top electrode of diameter of 1 mm. And these are the top electrode, and this is the WO3 thin film, and the bottom electrode, the FTO acting as a bottom electrode. We have done the current voltage characterizations using a Keithley instrument 2602 with a model number, and a compliance current of 1 milliampere was applied to protect the cell from the hard breakdown. The voltage wise was applied to the silver top electrode of the device on the probe station stage with the FTO electrode grounded. This is the comparison of the IV characteristics of the FTO-WO3 silver and the FTO-WO3 MOS2 device. And in the initial, we can see that the device initially is in the high resistance state. When we goes on increasing the voltage, the device switches from the high resistance state to the low resistance state, and it remains in the low resistance state. And when we reverse the polarity, and initially the device is in the low resistance state and return back to its high resistance state. It is termed as the switching from the low resistance state to the high resistance state is called as the set process, and it is called as the reset process. When the voltage is applied in the negative range, a sharp decrease in the current is observed at -1 electron volt. The set and the reset process are quite reproducible for a consecutive cycles under negative and the voltage sweeps, and these are the IV characteristic under dark conditions, and these are under the light illumination at 400 nanometer of the wavelength.
Okay, Salman, sorry, you have
Yes.
1 minute. Can you please?
Yeah, of course, sir. And when we goes on decreasing the wavelength, increasing the energy, the current get enhanced with a factor of 10 raised to power 2. But no such enhancement is observed in the case of that WO3 devices. Means that MOS2 is playing an acting role with the enhancement of the current of the order of 10 raised to power 2. This is the model for the resistive switching mechanism of the FTW3 and MOS2 devices. In this case, the sulfur and the oxygen vacancies makes a conducting channel between the top electrode and the bottom electrode in the case of the positive biasing, and in the case of negative biasing, this is the disruption, means the rupture of the conducting filament, which results in the change of low resistance state to the high resistance state. And this is the switching mechanism of the IV curves of the devices. Initially in the voltage range of 0.01 to 0.1, it's a linear ohmic region, and after then it follows the Child's law, a special limited condition. After then it is trap field limited conduction. After in this state it follows the ohmic behavior, and in case of negative bias region it follows mainly the ohmic behavior. And these are the endurance and the retention characteristics of the device. The current values in the low resistance state and the high resistance state is stable for the period of 10 raised to power 4 seconds. And for the cycles of endurance characteristic were performed for a period of 250 cycles. In this case, also the low resistance state as well as the high resistance state is stable, and the on-off ratio of both the state is around 10 raised to power 2. And this is the final conclusion. We have fabricated a memoristic device using WO3 MOS2 thin films using the thermal evaporation technique. The device showed reliable and the reproducible resistive switching with the on-off ratio of 100 and a retention time of longer than 10 raised to power 4 seconds. The device shows no degradation till 250 cycles, and the excellent optical switching properties are observed with increase in the energy of the light source. The resting switching behavior originates due to the formation and the depletion of the conducting filament that arise due to the diffusion of the negatively charged ions such as oxygen and the sulfur ions upon the reset and the reset process respectively. Thank you.
Thank you, Dr. Mohammed Salman,
Thank you, ma'am.
for your neat presentation. Any questions from the participants?
Any questions from anyone?
Any questions?
Okay, if there are any questions, just only one quick question.
Yes,
Mohammed, Salman, I could able to see that like some, thin films of MOS2,
yes, sir.
whatever you are preparing,
Yes,
which
sir.
makes a very uniform microstructures. Have you seen that? WO3 is has a
Yes.
very bigger grain size, whereas okay, after just MOS2, I
Yes.
could see that very uniform, and as well as some grain size they reduced a lot. Can you just comment on it?
No, on this deposition process.
So why so? I want to just know the reason behind it, because look at this 2 micrographs. It's seems different, right?
Yes, sir.
Yeah. Can you comment on it?
Actually, this is the SEM and the optical images of that WO3, and this one is the for the WO3 and the MOS films. Means you are saying that, sir, that in case of MOS2, the grain size is larger.
No, actually, yes, that's actually larger. It's very smaller. So
Yeah.
and also it's very uniform. So this also play an important role on switching part, right? So that's why
Yes, sir. Yes, sir.
It's okay. Don't worry. That's fine. Thank you.
Okay, sir. Thank you.
Yeah.
Thank you, Dr. Mohammed Salman.
Thank you, ma'am.
Thank you. Ma'am, we have Smitra.
Professor.
Tripati. Tripati, are you there? Hello? Salman, can you post your, can you
Yes, sir.
stop your
Okay, sir. Okay, sir.
Tripati. Mr. Tripati, are you there?
Yes, sir. Yes, sir.
Yeah, please share your screen. Salman, please close your screen. Yes.
Good morning, Professor Shah.
Hello, Professor Michael Short.
Michael Shah.
Good morning, Professor
Good
Lakshman.
morning. Good morning. Yeah, welcome.
Good to see everybody.
Yeah.
So we have only one more contributed lecture, Professor. Maybe after that we can start our lecture. We're fine. Okay, thank you so much.
Sounds good. Yeah.
Yeah, just 10 minutes.
Sounds good. Yeah. Thank you.
Yeah. Thank you. Tripati.
Yes, sir. Yes, madam. Can I say now?
Yes. Tripati is from Department of Physics, Rajiv Gandhi University of Knowledge Technologies, RK Valley. He is going to present on temperature dependent X-ray diffraction. Yeah.
Good evening, everybody.
Yeah.
Myself,
8 minutes for presentation.
Okay, madam. Now I am going to present temperature dependent X-ray diffraction as well as dielectric studies on Arvilla ceramics. So the body on the Arvilla ceramics here, ferroelectrics are basically Arvilla ferroelectrics are two types linked with the one perovskite linked with the chloride structure. Ca2O3 linked with the perovskite structure. Basically, this A side typically high cationic and whereas B side is lower cationic. This Arvillas is combined with some of the perovskite linked with the Arvillas. Among the reported Arvillas, this sodium bismuth titanate is one of the good piezoelectric high purity temperature, whereas some of the bismuth is replaced with second barium, calcium, titan, some of the small atomic radius. This will give you more effective when compared with the present compound. Therefore, in my present, I am going to present barium, bismuth, Ba, Bi4, Ti4, O15, Arvilla ceramic. It has a high purity temperature, orthodynamic crystal system. So my interest is to study the ferroelectric as well as phase transition studies from low temperature to high temperature. So this is the general formula of perovskite Arvilla space. So here there are a few number of systems are presented. First layer, second layer, third layer, fourth layer, fifth layer. Now I am going to present in fourth layer, 4-layer Arvilla space where barium, strontium, lead. Instead of strontium, barium, I am replacing barium. Instead of barium, just the motivation of the present work is so here, bismuth barium titanate ceramic, I have few drawbacks. One is this is oxygen vacancy is more dominated because of the high calcination and sintering temperature, which may induces the oxygen vacancies very more. To overcome these oxygen vacancies and particular ferroelectric properties and domain thinning walls, we are going to replace this bismuth by rarer elements like dyschromium, samarium, gadolinium. We did dyschromium, samarium, gadolinium. Among all these, at present, we are going to present only dyschromium at BI site. So this is the typical X-ray diffraction studies of dy dose to dBT system. So we have carried room temperature X-ray diffraction and refined with residual refinement, where we got the system is crystalline in nature as well as orthodynamic with 2-1A perovskite system. So we studied the surface morphology as well as index to understand the elemental analysis. So the surface morphology clearly shows that the system is it's a randomly oriented plate-like structures which is Arvilla space. The particle size is in the order of 1 to 2 micrometer, 1.14 to 1.58 micrometer range. So the elemental analysis also confirmed that it is highly pure in system. So we have by using reticle refinement data, we read on the unit cell. Here these are perovskite. The perovskite linked with this type of fluoride system. So this is the fluoride system. The D diagram shows the fluoride system. This perovskite is linked with fluoride. Therefore, these are the bismuth atoms replaced with some of the dy cells. So it is uniformly we got unit cell by using Vesta software once the system is purely refined. So we are also carrying temperature improve from X-ray diffraction studies from room temperature to 450 degrees centigrade to understand this ferroelectric transition exactly. So we carried from room temperature to 450 degrees. At near about to up to 3 degrees centigrade, we got all the systems are purely refined with orthodynamic with A21 phase. further going in between 380 to 450, there is existing two-phase system, both orthorhombic as well as pseudo-tetragonal system. Above 425 degrees centigrade, it's coming pure tetragonal with I4 by tubulum system. So this was carried by using reticle refinement with different temperature ranges. From that, this analysis we confirmed that the system is exhibiting below 420 degrees centigrade orthorhombic and above 420 is tetragonal system. To confirm this, we have carried its tolerance by using a temperature dependent X-ray diffraction data. We got all the lattice parameters various with the temperature. So this was explained with a tolerance. So to understand its mode vibrations, we have also carried temperature dependent Raman studies also. From the room temperature, we got 10 active modes of Raman active mode. These Raman active modes directly represent the system is pure in phase and Arvilas in phase. So to understand its modes of vibration, we also carried the temperature dependent Raman from the room temperatures to near about to 300 degrees centigrade. Within the temperature interval, the system is systematically decreasing with the lattice vibration systematically decreasing and more stable. Therefore, we confirm that system is pure in phase and more in stable. So we have carried dielectric properties in high temperature interval from room temperature to 500 degrees centigrade. So near about at 4 degree, 380 to 4 degree, the dielectric field systematically varies with respect to frequency, which indicates the frequency dependent dielectric properties. To understand this frequency dependent dielectric properties, we have carried Vogel pulsar fitting, so it shows that it is at activation energy 213 milli electron volt. This is due to the phonon vibration we got this expression. So finally, the system directly represents diffuse phase transition and ferroelectric to paraelectric phase transition near about 4 degree, 424 degrees centigrade. This was confirmed by using UV law as well as Vogel pulsar testing. So you also carry the temperature dependent PU loop. At room temperature, the system shows a slim and asymmetric loop, which indicates it can be useful for the energy storage application. If you go with increasing temperature, we also carry the temperature dependent PU loop. Near about 30 degrees to near about 70 degrees, the system is more stable in ferroelectric nature. If you go behind 100 degrees centigrade, the system is showing some of the irresponsible peak, which indicates its lossy characteristics more dominated above 100 degrees centigrade. Therefore, the system can be useful for ferroelectric property up to 400 degrees centigrade. Behind that, it will show the some of the leaky characteristics. Therefore, we can conclude that this system can be useful for 400 degrees up to 100 degrees centigrade ferroelectric property and energy storage applications. Finally, we can conclude that we are studying temperature dependent dielectrics as well as ferroelectric and Raman studies. From room temperature to 420 degrees centigrade, it shows ferroelectric property. Above 400 degrees centigrade, it's showing a paraelectric phase tetragonal phase that was confirmed by the temperature dependent dielectric studies as well as temperature dependent synchrotron X-ray diffraction studies. From room temperature, the system shows slim asymmetric loop, which indicates it is a ferroelectric property as well as application for the energy storage application. Thank you, sir.
Thank you, Dr. Tripathi, for your nice presentation. Any questions from the participants?
If you have any questions, please put in the chat box. Otherwise, you can raise your hand. I can allow you to ask the question. Is there any questions?
I guess I actually have one as well.
Yeah. Please, sir.
If you don't mind, yeah. So I noticed first of all, thanks for the cool presentation on these Aurelius ceramics. I've not seen them before. The structure, actually, which you can see on slide 15, reminds me of this rare earth barium copper oxide, which displays very high temperature superconductivity. Do you know or can you comment about the superconducting properties of these ceramics as well? Because the structure looks almost identical.
Yeah. Okay, Mr. Tripathi.
Sir, one second, please.
Yeah, the question is that actually, this kind of structures are well famous structure because it's called yttrium, barium, copper oxide based structures. That
Yes.
are very good actually high temperature superconductor, because that is a very important structure. Is this also similar structure? Do you have actually any comment on it?
It's not a superconducting material, but it has some of the piezoelectric properties. So because of the ferroelectric system combined with the chloride light, therefore number of chloride light increases, its ferroelectric become more strong. That is one of the advantages for this chloride light structure. But it doesn't have any superconducting property.
I see. Okay, thank you.
Thank you. And one more quick question. Suppose you can see this system, you're saying that from the high temperature XRD around 450 degree, it's going from orthogonal system to some tetragonal. But peaks, I couldn't see any variations on it, right? But how did you confirm it?
Sir, we confirm from the residual refinement by using actually this just
Yeah, but R factor is not that much change, right? What is the R factor?
almost. So
Yeah, I couldn't
near
see
about
any change in the
synchrotron,
peak, right?
yes, sir, synchrotron acted at near about 380 degrees centigrade. The peak position is just a random changes. So here exactly it coincides with. So the same system up to near about 380 degrees centigrade, it exhibits orthorhombic with the same system. Near about 380 degrees centigrade, it starts increasing that pseudo tetragonality.
Okay.
So in between 380 to 425 degrees centigrade, two-phase systems are coincide. Therefore, to confirm this system, we have carried temperature this residual refinement for a wide interval.
Okay. So you could not find any kind of indication in the higher angle side, right?
Sir, once again.
So you could not find any kind of deviations in the higher angle side too.
Yes, sir. A slight variation in the peak position, as well as this is very slight variation in the peak position only.
Okay. Okay, Tripati. Thank you so much.
Thank you, Tripati.
Thank you, madam.
Just a minute. Can you see my screen?
Yes, ma'am.
Yeah. Good morning, Professor Michael Schott.
Good morning, everybody.
Yeah. He is from Massachusetts Institute of Technology, USA. Invited lecture 42 of session F5F. He is going to present on measuring material damage with stored energy, applications from nuclear reactors to non-proliferation. He has research interest on development of fouling resistant materials, in situ mesoscale nuclear material science and transient grating spectroscopy. He has received many awards and achievements. Junior Bose Award for Excellence in Teaching, National Science Foundation Faculty Earlier Career Development Award, Earl Murman Award for Excellence in Undergraduate Advising MIT, Ruth and Joel Spera Award for Excellence in Mentoring and Advising, Best Poster First Annual MIT NSC Research Expo, Best Nuclear Energy Presentation, Second Tokyo Tech, Best Graduate Paper, Bodycott 2009 Paper Prize Competition. Welcome, Professor Michael Schott. And you have 25 minutes for presentation.
Thank you very much,
Thank
Professor
you for
Lakshmanan.
being here in ICON 2021.
Oh, it's my pleasure. Thanks, Professor Lakshmanan.
We are honored to have you.
And thanks everyone for having me here. Is the audio coming through okay?
Yes, Professor, you can carry on.
Great, okay. In that case, I think I'll launch right into it. I'm going to tie into the nano theme of the conference in a little bit different way than most have by measuring nano energy for the purposes of nuclear non-proliferation. And I'll be presenting on the energetic fingerprints of the tiny amounts of radiation damage. First, I'd like to acknowledge some of the sponsors of this project. This started as a collaboration between MIT and the Singapore University of Technology and Design, and they funded this work when no one else was willing to. Back when this was just a crazy idea, and other sponsors said, "Oh, I don't believe this is possible." They provided the seed money, that was eventually picked up by the US National Science Foundation and the National Nuclear Security Administration as part of this consortium for enabling technologies and innovation. So the question we're trying to get at is, what is the lowest radiation dose that can give us useful information with implications for nuclear security? Back when I started this project, the year was 2015, and the US had just entered into what's called the Iran nuclear deal, where Iran agreed not to enrich its uranium to the point of making nuclear weapons, and there was to be a way to verify this deal. And that was supposed to be a path towards peace between the US and Iran. As some of you may know, our former president, who shall not be named, got out of this deal, and now our new president is hoping to get back in, which means that this research might have some applications again. And the technical underpinning of the ability to verify uranium enrichment, if you look inside, if you come from inside the centrifuge, the way these work is a supply of UF6 gas, uranium hexafluoride, flows into this spinning drum. So this is spinning at up to 100,000 times per minute, separating out the heavier isotopes on the outside, while the lighter isotopes on the inside get sucked up by partial vacuum and move on to the next centrifuge. Now, at the walls of these centrifuges, UF6 gas is constantly bombarding them with alpha particles. This is about 4.5 MeV radiation. And the goal is, if we can measure this radiation damage in a standard instrument like a calorimeter, then we have a way of knowing how much gas was there for how long and how many weapons worth of uranium were made in the centrifuge. So this is how we believe we can verify this non-proliferation treaty and see whether Iran is living up to its end of the deal. Now, of course, history tells us something different. The US walked out of the deal first. Hopefully, we walk back into it very soon. So the technical underpinnings of this is that this centrifuge is full of uranium-235 and 238 hexafluoride gas molecules. 235 is the weapons grade isotope. 238 is the fertile or the non-weapons grade isotope. And once in a while, every one of these uranium atoms will emit alpha particle and a daughter nucleus. And this alpha radiation damages the outside walls of the centrifuge, leaving a signature that we call the stored energy fingerprint. The two questions we want to answer to verify these deals are: how much uranium was made and what was its enrichment? How much uranium tells us how many potential weapons there could be. Knowing the enrichment tells us whether this uranium is used for peaceful purposes, for reactor fuel, or for military purposes for weapons. And inside this wall, if we zoom in, the alpha particles do damage as they travel through the inside of the material with a finite range. It's a very small volume. It's about a 20 micron depth, and it's an extremely low fluence, a number of alpha particles, just up to 10 to the 11 alphas per year of processing 90% enriched uranium. This is about 10 orders of magnitude lower than in a nuclear reactor. So this is an absolutely tiny amount of radiation damage. And the sensitivity question we ask ourselves is, how low can we go? How little damage can we sense? Now, when we started looking into this problem, we realized that uranium-235 and 238 are relatively stable isotopes. They have very long half-lives. However, uranium-234, which is produced by the decay of 238, has a much shorter half-life. And by modeling the number of alpha particles we expect out of the centrifuge and realizing that most of them come from U-234, we constructed a model of the total amount of damage as a function of enrichment and realized that almost everything was due to this U-234 isotope. So now we know what the alpha energy we're looking for is. This sets the range of the radiation and tells us something that will help us define our stored energy fingerprint. The important part here is that almost all of the damage comes from this uranium-234. This is not a naturally occurring isotope. It comes from the decay of 238 into 234. And so we use, we're going to focus on an energetic aspect of radiation damage. There are two possibilities for us. We could look at what's called Wigner energy. the formation energy of actual defects, which has about 0.1 to 2 joules per gram in most materials. This is a very low amount of energy, and we deem a little bit too difficult to start out. Instead, we're going to focus on phase transformations, even if in very small amounts of material, because they store 1,000 times more energy. So if radiation damage can induce a phase transformation, even on the nanoscale, and we can measure it, our signal is about 1,000 times stronger. Now, looking at the materials of construction of a centrifuge, they're often made of an aluminum alloy, like a high-strength aluminum alloy, connected with stainless steel 304 piping, and the seals between them are gaskets made of a material called PTFE or Teflon, if you've heard of that. We're going to focus on Teflon first, since as a polymer, it's very chemically susceptible to radiation damage. We use two techniques in order to analyze the damage. One is called differential scanning calorimetry, or DSC, which I'll explain on the next slide. We actually extract little discs of material from a strip of PTFE. Notice that interspersed among all these different irradiated pieces are control samples, unirradiated ones. And that's because depending on the location, the energy of phase transformation of PTFE is variable. It depends on the processing parameters, on how much it was squeezed, on the temperature during processing. And we punch out little discs about 50 microns thick, and we irradiate them with 4.5 MeV helium ions from a linear accelerator we have at MIT, doing damage to about halfway through the thickness of the material. We're also going to use flash DSC, which is another version of DSC, but it operates about 1 million times faster with 1 million times less material. So we can actually measure samples as small as 1 nanogram, and we can measure the energetic changes from this. Now, to explain how DSC works, it's a heat capacity measuring tool. Inside this instrument right here, there are two very small pans of aluminum. One we keep empty, we call the reference pan, and one we call the sample pan, in which we put our material. And we measure the amount of power required to keep these two pans at the same temperature. Because this pan contains a little bit more material, it takes a little bit more heat to get it to the same temperature. That excess heat in a normal material is the heat capacity. If that excess heat changes from its normal heat capacity, then this could indicate radiation damage, new phase transformations, or other features for us to look at. And the signal that comes out of DSC looks something like this. We get a heat flow normalized in terms of power per gram as a function of temperature. And as you start applying heat to the system, there's a stabilization point. There's a baseline heat capacity where, let's say it takes 0.3 watts per gram to heat this material up. This is the heat capacity of PTFE. And then if a phase change happens, you'll see some sort of a peak that will indicate a lot of energy absorbed in order to change the phase of the material. And then you can continue heating to establish this baseline. Draw a baseline, whether it's a linear fit, a polynomial fit, it doesn't really matter as long as you're consistent. And integrate the peak underneath to get things like the enthalpy of melting or the enthalpy of recrystallization and the onset temperature of these curves. Watching these parameters change is how we construct our radiation stored energy fingerprint. And so to review a little bit, we punched pieces of this PTFE. Some of them we left unirradiated and measured those as a control. And other ones we irradiated to very, very low fluences of alpha radiation. With this one right here, 10 to the 11 alphas per square centimeter, corresponding to a couple weapons worth of enriched uranium. We measure between 250 to 375 Celsius. We heated at 10 C per minute. We watched the heating and the cooling curve. We performed everything twice for repetition. And by measuring the control, the unirradiated enthalpies of crystallization everywhere, we construct a control surface for this physical sample. And that way we can be confident that whatever changes we measure are actually due to radiation and not due to sample location. For a little bit of the physics behind what's going on when you radiate Teflon. It starts off as a linear fluorinated polymer. When you add radiation, you can cause cross-linking of these polymer chains. You can knock off a fluorine atom, and then nearby chains can join up and bond, changing the molecular nature of this cross-linked PTFE. And again, we're focusing on these gaskets that connect the centrifuges because all the gas has to flow past them, irradiating them as they go by. So now let's get into the results. What we noticed was a pleasant surprise. The enthalpy of melting and the enthalpy of cooling was visually separable from the control. The unirradiated in gray, you can see many, many curves overlap quite well. And once we get to a dose of about 10 to the 9 ions per square centimeter, or 1/10 worth of nuclear weapon, we can start to see some visible deviation. And in fact, to zoom in this recrystallization peak during cooling, you can actually see that with these to 2 sigma, you can make a statistically significant differentiation between peaceful low-enriched uranium and weapons-grade uranium. So by making the simple measurement from the surface of these gaskets, we can tell whether the centrifuge was used to make reactor fuel or weapons fuel. And so if somebody says, oh, we only made reactor fuel, we can verify that statement. The mechanism which causes this change in enthalpy is due to the structure of PTFE. So it consists of a lot of these sort of block crystallite chains linked all together, but inside there are some of these amorphous regions where the chains are a little more loosely packed. And when you apply radiation damage to this structure, you can break some of these crystalline chains, inducing more amorphous region and causing the material to crystallize more easily as it cools down. And this change in crystallization enthalpy and temperature is exactly what we track using these DSC measurements. Now, what about verifying the enrichment level? I showed you here what the damage level looks like as we fire alpha particles into our PTFE. This is not actually what happens inside a centrifuge, because these particles are monoenergetic and unidirectional. This is an artifact of the accelerator. In reality, when you have a UF6 gas irradiating this material in all directions, you end up with a damage profile that looks something like this. From a monoenergetic omnidirectional gas, it's a flat profile with a very sharp defined range. If we can reproduce this profile by cutting this piece of PTFE into tiny little micron-sized segments using a microtome or cryomicrotome, and we can measure that stored energy, then we could verify that it was indeed an alpha particle of the right energy that caused the damage. But this mass is 1,000 times too small to use in DSC. So we have to switch instruments. So instead, we're using one of the world's first nanocalorimeters. This is a calorimeter on a chip made by Mettler Toledo. I think we bought the serial number 20, something like that. And on this little chip, which is just 25 millimeters in size, there are 2 MEMS devices, each of which contains 16 thermocouples and 4 heaters. It's a calorimeter on a chip. On one of these, we place our tiny little sample, which can weigh as little as 1 nanogram. On the other one, we place nothing. And this functions as the reference calorimeter. We can either use a microtome or a focused ion beam to cut out a tiny little piece of this irradiated Teflon or whatever you want and place it in the center of this nanocalorimeter. And we are, I believe, the first group I've seen that's doing this. There may be others, but they haven't published it yet, so who knows? But we're very excited to be one of the pioneers in this new type of technique. To verify that the instrument actually gives the correct results, we took a little piece of indium, a 7 micron thick foil of indium, and verified its enthalpy of melting by measuring its dimensions, because we used the focused ion beam to measure its dimensions, multiply by density, and get a mass. And we also looked at the enthalpy of melting and the energy signature from this calorimeter, and we obtained the same mass within limits of error. So we know that this technique is returning the correct energy in an absolute scale. And finally, for the fun part, I want to reintroduce the microtome method of extracting micron-thick samples of this PTFE. We irradiate our Teflon with a 500 microcurie source of polonium. This is like an accelerator that fits in your pocket, but you shouldn't put it in your pocket because it's radioactive. What it does is it fires alpha particles in all directions from the polonium source, simulating the UF6 gas. We then have a little piece of material that sticks out from the sample. So this is a 250 micron cylinder of Teflon. We slice off sub-micron pieces, put them on the calorimeter, and heat them up and watch the enthalpy of phase transformation. And I'm pleased to say that what we get in the flash DSC very clearly mirrors the damage profile we would expect from theoretical what happened. And so what's really even great about this is I've superimposed the energies that we measured by bulk DSC, and they agree fairly well. The unirradiated agrees perfectly. The irradiated is a little bit different, so there's some sort of a offset between the two techniques. But most importantly, right at the range of uranium-234 alpha particles, the extra stored energy stops. So this allows us to verify both the amount of alpha particles and the energy of alpha particles, making it difficult for a bad actor, whether it's Iran or the US, to fake out the results, to give fake material to the inspectors. This means that you can't fool them. And so when the IAEA, the International Atomic Energy Agency, heads in to inspect pieces of centrifuges, they can measure both the total energy and the range of that energy to verify that it came from the right isotope of uranium and that it wasn't faked by using an accelerator or some other means. And so that's where we are as of today. These results are quite new. We only got this result 3 weeks ago. So I don't really have a conclusion to tell you because this is all unpublished stuff. It's very new. We don't know 100% if it's real. That's going to depend on peer review. But we'll be submitting this for publication soon, and you guys get to be the first to know. So I'll stop there, and I'll take any questions you have now.
Scintillating talk, Professor Mike. First time nano DSC. First time I'm hearing about this nano DSC. It's very nice.
Oh, cool.
Wonderful stuff. Any questions?
If there are any questions, please post your questions in the chat box. And before, if I get actually some questions from the audience, I'm very interested about this work, and I would like to know, so what is the maximum amount of actually heat radiation is coming out from those pipelines?
Oh, sure. So to go back to the diagram of the centrifuge pipeline, right?
Exactly.
Yeah, the centrifuges operate at between 60 to 80 degrees Celsius, but all that heat comes from spinning, actually. This is friction in the gas from spinning at about 100,000 times per minute. The actual heat released from the radiation damage is effectively zero. That's what makes this so difficult. Is in a reactor, the radiation can cause things to increase by hundreds of degrees Celsius and do tons of damage. Here, we're talking 10 orders of magnitude less in all regards. So this is nano amounts of damage, nano DPA, nanojoules imparted into the material. And the one comment I got when I was trying to get this funded is you'll never see anything. It's too small. I'm proud to say that those people were incorrect.
Okay. Because in the nuclear reactors and all, if you can see, it's maybe almost 400 to 500 degrees centigrade. You'll get at the pipelines. Okay, there we can't use this Teflon because this PT, Fe, and so on. Because this melting point of this one is very less, right? So you're intentionally use this Teflon. So I was wondering that why it is how much radiation is coming.
Sure, yeah. So if you take the 400 or 500 C and divide by 10 orders of magnitude, you're now talking about a microkelvin increase in temperature due to the radiation.
Yes, yes.
Yeah. The real increase is from friction in the gas, but that's limited to 60 to 80 Celsius to stay. The PTFE melts at 425 Celsius. So we stay well below that.
Okay. And can you just can you brief that how this alpha particles interaction with this PTFE, what kind of some crystallization or actually how does it changes its bonding, and our heat capacity which you have measured, how much it is?
Sure. So one of the ways in which it changes bonding is shown here.
Yes.
The PTFE usually has quite linear chains that are folded up on themselves. The area that radiation damages is about 5 nanometers in diameter, and that can encompass the nearby chains. So if you knock out a fluorine atom ballistically, and there's a free end of a Teflon chain, it can cross-link up. This is a structure that's not normally observed in PTFE, but it can be caused by radiation damage. It can also cause chain scission. In other words, there are kind of two big things that could happen here. One of them is to join other chains. The other one is to cut them. And so you make many smaller chains, more cross-linking, and that's what contributes to the heterogeneity of the structure, which makes it easier to melt and harder to cool, changing the enthalpy and the temperature of those transitions.
Okay, Professor. Thank you. Thank you so much. Is there any
pleasure.
questions from? Thank you. If there is any questions, please post in the chat box, or you can raise your hand. I can allow you to ask the questions, participants.
Yeah, if anyone is interested in collaboration, by the way, since we've got one of the only instruments right now in the world, there's maybe only a few dozen or so. If there are new polymers you're looking to get phase transformations for, but you're worried about their, about them being explosive or fragile or something like this, the heating rate in this flash DSC is up to 2.5 million Kelvin per minute. So if there are materials for which you want to know enthalpies of phase transition, but they're not stable at temperature, we can raise them up and down in temperature to 500 Celsius in 5 milliseconds, preventing damage, oxidation, decomposition, and still getting the energies of this. This is also done in an inert atmosphere. So if anyone's interested in collaboration, please feel free to email me. I'll put my email in the chat just so everyone's got it. And while people can't go across borders now, samples can, and feel free to send me anything that you're interested to characterize.
Yeah, thank you so much.
Thank you, Professor Mike.
Thanks for having me, yeah.
So nice of you to invite collaboration.
Participants, is there any questions from your side? Seems there is no questions. You can.
Thank you, Professor Mike.
Thanks for having me. My pleasure.
Yes.
Yeah, you can just conclude your session now.
Yeah. Thank you. Thank you all the participants, and thank you Dr. Tripathi and Dr. Sumitra, Dr. Mohammed Salman Siddiq for the contributor lectures, and Professor Michael Short for the invited lecture. Thank you all. Thank you, Dr. Suresh Perumal.
Okay, thank you. Professor L. Sudha, Madam, firstly for chairing this session. So on behalf of ICON Organizing Committee, I thank you, Professor Michael and Professor L. Sudha, for organizing and conducting this session 5F. Okay, thank you all.
Thank you so much.
Thank you.